Hey everyone, this video is part of Unit 3, Lesson 2 on writing large numbers using scientific notation. Before you start, make sure that you have paper and a pencil or your notes packet to take notes. Remember that while you're watching, you can pause and rewind as needed. Let's start. At the end of today's lesson, there are 2 learning targets. You should be able to say, I can express large numbers using scientific notation, and I can determine how many times larger or smaller a number is compared to another expressed in scientific notation. First, let's look at this table. It's comparing different forms of patterns of numbers in scientific notation. It starts with power of 10 that we're familiar with, then a value, then something new for today, scientific notation, and how you would read that number. The first one, 10 to the second power, is the base 10 multiplied by itself twice, so a 10 times 10, which gives you a value of 100. To write that number in scientific notation, it would look like 1.0 times 10 to the second, and we read it as 100. 10 to the third is 10 times itself 3 times, 10 times 10 times 10, or 1,000. And in word form, we would write it as 1,000. In scientific notation, 1.0 times 10 to the third. Then the next one, 10,000, looks like a 10 with 3 more zeros. That is 10 to the fourth power because it's a 1 followed by 4 zeros. In scientific notation, it's still a 1.0, but now 10 to the fourth and 10,000. The next one has a value of 100,000, which is 10 to the fifth, and is written as 100,000. The number out front still is that 1.0 times 10 to the fifth. Then 10 to the sixth is a 1 with 6 zeros that looks like that, and is called 1 million. And in scientific notation, 1.0 times 10 to the sixth. Then a 1 with 9 zeros is 1 billion, could be written as 10 to the ninth, and in scientific notation, 1.0 times 10 to the ninth. And finally, 1 trillion, 1.0 times 10 to the 12th, is a 10 to the 12th, or a 1 with 12 zeros that looks like that. What you should notice in this table, as the exponents get larger in the first column, the values also get larger in the second column. Then in all of those scientific notation, since all of the numbers started with a 1, they're all written as 1.0. Consider the number 2 million. What power of 10 represents 1 million? Well, on the last slide, we said that 1 million was 10 to the sixth power because it's a 1 with 6 zeros. Complete the multiplication sentence to express 2 million using this power of 10. This is the first time we're not going to see a 1.0 because it starts with a 2, this time it's a 2.0. It still has 6 zeros, we're moving it 6 times, so it's a 10 to the sixth power. Scientific notation is a method of writing very large or very small numbers using exponents, in which a number is expressed as the product of a power of 10 and a number that is at least 1 and less than 10. So that number out front, that decimal like here, is going to be larger than 1 but smaller than 10. 2.0, 5.4, 6.11, 7.551. A number bigger than 1 but smaller than 10. So let's look at some numbers that are and are not in scientific notation, and this should help you with the quizzes assignment that you'll have at the end. For example, in scientific notation, you could say 9.3 times 10 to the fourth power. But if I change just one thing and made that 93 times 10 to the fourth power, now it is not in scientific notation. This is not in scientific notation because this number up front is too large. It is bigger than 10. Then another example in scientific notation, like 7.26 times 10 to the eighth power. It's okay that there's more numbers after the decimal, but I just need that 7.26 to be bigger than 1 and smaller than 10. So if I made it 0.726 with the decimal out front. It would again not be in scientific notation. This time the number out front is too small because it's smaller than 1. So in scientific notation, that number out front, like 9.3 or 7.26, is at least 1 and smaller than 10. Another example in scientific notation could be 4.3 times 10 to the 9th power. It looks like the other ones, written well, but if I change it to 4.3 times 9 to the 10th power, that is not in scientific notation. The base number that we're multiplying here always has to be a 10. In scientific notation, that's the only number that works, so a 9 would not be. It looks like maybe we accidentally mixed up the 10 and the 9 here with the base and the exponent. The expression 20 times 10 to the 5th is also equivalent to 2 million. Use the definition of scientific notation to explain why 20 times 10 to the 5th is not the correct expansion or expression of 2 million in scientific notation. Even though they're equal to the same number, this number is not in scientific notation because of the 20. Numbers in scientific notation have to be between 1 and 10, so the 20 is too big. I would need that decimal to be between the 2 and the 0 to be written correctly. Consider the standard and scientific notation of the numbers shown in the table. Describe the similarities and differences between the values expressed in scientific notation. Pause here for a few seconds while you jot down some ideas. How are these numbers the same and different? You probably noticed that they have the same amount of numbers. They have 7 digits. They're in the millions, and they use the digits 2, 3, and 0. So as long as you have something like that in your notes, you're good. It does not have to be word for word. Then the differences is what we want to focus on. In this one, the 3 and the 0 have been switched. So one of them is 2,300,000 and one of them is 2,030,000. The one on the top does not need a 0 in scientific notation. Notice that this 2.3 does not need any of these zeros after it, but this 2.03 does need this 0. Because it's between two non-zero numbers, the 2 and the 3, I have to keep that 0 when I'm writing it in scientific notation. And then we don't need the zeros at the end, just like above. Now let's do some practice. The table shows the number of visitors to several amusement parks in Florida in the year 2019. Express each value in scientific notation. We're going to do it in parts. First, we want to know where to put our decimal. We need to put it between two numbers so that it's bigger than 1 and smaller than 10. So there's only one place we could put it. In the first number, it would go between the 2 and the 0, making it 2.096. I need all of those non-zeros. Animal Kingdom, it would go between the 1 and the 3 to make it 1.39. In Busch Gardens, between the 4 and the 2 to make it 4.2. In SeaWorld, between the 4 and the 6, 4.64. And in Adventure Island, between the 6 and the 5 to make it 6.56. All of those numbers in green so far are in scientific notation because they are larger than 1 and smaller than 10. Then, scientific notation is always times a base of 10, so we can go ahead and put that for all of them. That's what helps us easily move our decimal left and right, so the only base that'll work is a 10. Then we need an exponent. All of these are very large numbers, so they're going to have positive exponents. The exponent comes from how many times you move the decimal, but not how many zeros there are. Most of the time, those will not be the same answer. I'm going to say it again. The exponent comes from how many times you're moving the decimal, not how many zeros there are. So in this large number, 20,960,000, the decimal is at the end. It's invisible right now. And I'm going to move it to where we had that green line. 1, 2, 3. I'm not counting the comma. 4, 5, 6, 7. I moved it 7 times, so it has an exponent of 7. In Animal Kingdom, I'm going to move it 1, 2, 3, 4, 5, 6, 7 again, so another 10 to the 7th. For Busch Gardens, 1, 2, 3, 4, 5, 6 times, 10 to the 6th. For SeaWorld, 1, 2, 3, 4, 5, 6 times again. And for Adventure Island, 1, 2, 3, 4, 5. All of those answers are now complete. They've got that green number in front between 1 and 10, then multiplying it by a base of 10, and an exponent depending on how many times you needed to move the decimal to get it there. Pause here if you're still writing. Complete the table. It's going between scientific and standard form. Pause the video here for a second while you copy and complete. Let's see how you did. The first number, 200, would be a 2.0, which could also just be a 2. 2.0 is not wrong, but 2 is a better answer because it's more simplified. Then we would have moved it 1, 2 times, so times 10 to the 2nd. You should have also been able to do the last one, which would have been a 2, times 1, 2, 3, 4, 5. Notice that these do have the same number of zeros and exponent, but that doesn't always happen. Because there aren't any other non-zeros is why we move it 5 times, and it's an exponent of 5. What about the other way? Were you able to figure out how to get it from scientific notation to standard form? 10 to the 3rd, I'm going to move that invisible decimal 3 times. So if it starts here, 1, 2, 3, I'm going to fill them in with zeros, and that would be the number 2,000. 2 times 10 to the 4th is going to be 20,000. Maybe you just followed the pattern, maybe you caught on with moving the decimal, but pause here if you're still writing. I'm going to skip these slides, and then will you pause here while you try to do that again with just the table part. Change those numbers between scientific and standard form. On the top one, if you move it 4 times, there are not 4 zeros. So it was the number 2.1. The 10 to the 4th tells me I'm moving it 1, 2, 3, 4 to the right. I'm going to fill in with zeros, and there's only 3 blanks there, so 3 zeros. That answer would be the number 21,000. Then in the second one, 420,000, I'm putting the decimal between the 4 and the 2. It's always times 10. And I'm going to count 1, 2, 3, 4, 5 spaces, so 10 to the 5th. And 8.4 times 10 to the 6th, I'm going to move it once, and then I need 5 more zeros, so 84 with 5 zeros, which is the number 8,400,000. And our last one. Each statement contains a quantity. Rewrite each quantity in scientific notation. There are about 37 billion cells in the average human body. In scientific notation, we would put that decimal between the 3 and the 7, making it bigger than 1, smaller than 10, multiplying it times a base of 10. Then I'm counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places, so times 10 to the 10th power. There are about 3.7 times 10 to the 10th cells in the average human body. Light travels through space at a rate of 300 million meters per second. I'm going to place that decimal between the 3 and the 0. It's not wrong to write 3.0, but a better answer would just be a 3. Times 10, and we moved it 1, 2, 3, 4, 5, 6, 7, 8 times. 3 times 10 to the 8th. You should now be able to complete the newly assigned quizzes assignment. It's called Quizzes, Scientific Notation. It has large numbers. You need an 80% or above, and you do have multiple attempts. There's also one other assignment that's open this chapter. You should already have completed the Edge Excel. Once you're finished with both of those, remember that you have 3 options this chapter for iReady. You need to pass 1 lesson to earn a 10 out of 10, or pass 2 or 3 lessons to earn extra credit. Good luck!